Okay, so let's now see quickly the local inverse theorem, which is kind of related to the implicit function theorem, except that now we talk about more than just two variables. It can be any number of variables, and we talk more precisely about invertibility of the function locally. Okay, so local inverse theorem. Let's read that together. Okay, so we have a function f that acts on an open set in Rn with image in Rn. That is important because we will be able to describe the inverse functions only if on open sets. Okay, if you want to work on specific closed sets, you have to refine your study. So from open sets included, sorry, not belong, included in Rn. And we already said that, but very quickly, that if I wanted my function to be invertible, it means that, in a sense, applying the function doesn't make you lose any information or gain anything new. It means that in terms of dimensions, that's a very vague way to state things, but that's something maybe you can keep in mind. It means that the number of dimensions of the entry has to be equal to the number of dimensions of the output if you want to be able to reverse the process. If you lose information, meaning if the dimension of the input is greater than the dimension of the output, you're losing information somewhat, so that you will never be able to rebuild completely the entry information. And if ever you go to bigger spaces, then you will have too many choices to get back to your original function. So, and by the way, let's make it clear that f is invertible or locally invertible if we can find an inverse function such that which is defined as you compose it with the function and you're back where you started. Okay, and well, whichever way you want to do that. Okay, and here we're talking locally. All right, that has its importance. So you consider some neighborhood around a point x0. Okay, so you've got your point x0. Sorry, x0 that belongs to you. What this theorem says that there exists a neighborhood around x0. Okay, so you remember what does that mean? It just means a small open ball around x0. So if x0 is just a real number, it's going to be a small interval. If you are in R2, it's going to be a small circle. If you're in R3, it's going to be a small sphere. And whatever extension you can do of these notions in Rn. Okay, so there exists a neighborhood x0, and there exists a neighborhood around y0 where we have that f of x0 is equal to y0, and it gives you conditions such that so if f takes this neighborhood around x0 to the neighborhood around y0, there exists, okay, a function f minus 1 that goes from the neighborhood of y0 to the neighborhood of x0, and that would be the local inverse. I insist on the idea of locality because that's the condition is actually going to rely on the Jacobian of the function f. All right, so what does that theorem says? The theorem says that if the Jacobian matrix of f at x0 is invertible, and so you know, of course, the Jacobian is going to be a local matrix because it depends on the x you are located at. So invertible means you know that the determinant is not 0, then f is locally invertible. Okay, so that's pretty simple idea to use. Okay, and we have some more conclusions to this theorem. It tells you that the inverse function f minus 1 is then continuously differential, and its Jacobian matrix at y is equal to f of x0 is the inverse of the Jacobian matrix of f. But this we had already stated. Okay, and you would even have a global inverse theorem, which is not stated in that document. So maybe we can write that global inverse theorem. We need the Jacobian of f to be invertible everywhere. Okay, we need to have a local inverse everywhere, plus maybe not easy to show the fact that f is an injection. Okay, all right. And if it's not an injection, and you know that it's half of the way to prove that something is invertible, you will never get that it's invertible everywhere. Maybe let's illustrate that with some example that we incidentally saw during class, during our worksheet on partial differential equations. We had used that following substitution. We had put u is equal to x plus y and v is equal to x times y. Okay, and the idea was that actually we were working on a domain which was the set of x, y in R2, such that x, I think which ones did we have? We wanted x smaller than y. Okay, but if you choose or x strictly bigger than y, that would work also. Okay, and I told you, well, at least to the people I had in tutorial, and by the way, I always record my tutorial, so you can live stream them later. Well, not live stream, but stream them later on if needed. I had told that, well, you couldn't see yet why that was a requirement, except from the fact that at some point in the exercise you had to divide by x minus y, so you needed x to be different from y. But it is also related to the fact that if I want to make a substitution, we need to have a valid substitution. What is a valid substitution? It's something that takes your set of variables, let's say it's x, y, and that gives you a new set of variables, let's call them uv, but it's going to be a good substitution if and only if you can get back to the original variable, okay? If you've got phi that takes you from xy to new variables uv, you want to be able, usually in the end, to reverse the process, okay, to be able to go from uv to variable xy. So that's why this is very closely related to our idea of inverse theorem or local inverse theorem. If we want to prove that we have a valid substitution, we would like to prove that we have this change of variables here can be inverted. Okay, so if we use directly our theorem, what do we get? Okay, if we use directly our theorem, we make the Jacobian matrix, so let's call that phi, okay? And we get that phi of xy defines u of xy and v of xy, okay? So phi acts from R2 to R2, right? And more precisely, well, from D to some part of R2 that we're going to see later. Okay, so we've got the Jacobian of phi. You know, it's going to be the gradient of u, so that's going to be 1 for the du over dx, 1 for du over dy for the first row, gradient of v for the second row, so that's going to be y and that's going to be x. And if I compute the determinant of the Jacobian of phi, sorry, determinant, that's going to be x minus y. So I want to be able, in order to be able to apply my theorem, I want x different from y. Okay, and if we want to keep the plane, well, the area where we're going to act into one single piece, so if that's x and that's y, we will want to exclude that line and half of the plane that it is determining. So if we make the choice x has to be smaller than y, that means that we're going to stay on that area. Okay, x is smaller than y, right? And so with this in mind, then we can apply the local inverse theorem and say that I need my set to be opened. That was important. So if I need openness, I will need to have a strict inequality. So xy in R2 such that x is smaller than y. Okay, I can apply my local inverse theorem on that open set again, so maybe I should write it in big letters. We need our sets to be open, and then I know that locally I will have no problem about this. Okay, I can find a local inverse, and actually we can even find it very clearly, right? So maybe that's going to remind you of something. We've got u is the sum of x plus y, and v is the product of xy. Maybe you remember that this means that x and y are solutions of the polynomial given by, if I use a capital X, 2 minus u x plus v is equal to 0. Okay, our roots of this polynomial, so more than solutions, it doesn't really mean to the polynomial equation. All right. Okay, so x2 minus ux plus v is equal to 0. So in order for this polynomial to have the two roots, we need the delta to be strictly positive. Okay, so we need u squared minus 4v to be greater than 0. So that's one part. And then in that case, we've got x and y that are going to be given by u plus or minus. So if we chose x to be smaller than y, it's going to be minus square root of u squared minus 4v over 2, and y is u plus square root of u squared plus 4v over 2. Minus 4v, sorry, over 2. And you see, we needed to decide whether we wanted x smaller than y or y smaller than x, because I could absolutely exchange the values of x and y. Okay, so and that, but the problem is that in the plane, that's if x is the first one and y the second one, or the contrary, it gives you two different geometric locations. So I really needed to restrict that in order to have a good injection. Otherwise, I wouldn't have had an injection, because the value, the first value, second value, or second value, first value would both be solutions of my equation, right? And reverse the process of substitution. And if you want to go just slightly further, let's, sorry about this. Let's show that in the xy plane, you have this location, so that's x smaller than y, and that sends you in the uv plane something that is going to be separated by u and v. So for v is equal to 1 over 4 u squared, so something looking like a parabola. V is equal to 1 over 4 u squared. Okay, that is coming from this part. All right, and then what part of this is defining? So I want it's going to be that area. So that transformation sends this half plane into that